functions, right? As many of you know, functions actually, they describe what we can see around us. They're actually a tool which can be used to describe, the real world, that too in mathematical terms, right? Whatever we can observe around us, if you want to just, if you want to analyze it, if you want to give some conclusions about it, we'll try to represent them in terms of functions, right? And normally function can be represented by either an equation or a graph or a numerical table or sometimes as a verbal description, right? Understand, probably most of us are familiar with describing functions by an equation. But now let us try to see in other terms also. Okay, and see, these are few examples for what functions are, right? See, if you take an example of interest paid on a cash, you can see in first one there is two different situations, in fact two different quantities, right? One quantity is interest paid on cash, and see that actually depends on the time of investment, right? How long you are taking the money, depending on the time your interest will increase. So interest depends on the time. So interest can be represented as a function of time. That's how you can interpret the first example. And if you take the second one, you see area of a circle depends on the radius of the circle, right? As we know, the definition right, as we know, the definition of the formula for area of a circle, you see it is A is equals to pi r square, if you remember correctly, right? So if you know the radius of a particular circle, you can easily find out area of a circle. So area is one quantity here and radius is the other one. And particularly here, if you observe, area depends on radius. So you can represent area as a function of radius. Then similarly, if you calculate the distance an object travels at a constant speed along a straight line path depends on the elapsed time. So here the distance traveled depends on elapsed time. So you can represent a distance, in terms of time here. So these are all some simple examples which you can see around us, to represent in terms of mathematical terms or in terms of functions, right? Then I'll share you this PPT as well as the notes related to this. And if you want to just, sometimes, we may discuss some points which are not part of this particular PPT. So those points, or else if I give you some other examples, some problems, you can just take them as notes, right? And see, in all the examples what we discussed till now, we are simply saying there are two different quantities. Let us say some quantity A and quantity B, and quantity A normally depends on quantity B, so that we can represent quantity 1 in terms of quantity B, right? Normally, instead of saying quantities are A and B, we'll simply take them as X and Y, right? We'll simply take two different variables in mathematical terms. One variable is X and the other one is Y. And to represent any function mathematically, we'll try to write Y as a function of X, right? So we'll simply write Y as a function of X. As you can see here, to represent a function, there must be two quantities or two variables, as you can see here. So we'll take one as X and the other one as Y here. You can see this variable Y is actually depending on this variable X. And we just write symbolically a function as Y is equals to f of X, and we'll even pronounce it as Y equals f of X, right? So that's how you can understand here. And when you write a function with this notation, so this f represents a function, and you see the letter Y or else the variable Y. Since, when you write Y is equals to f of X, as many of you know already, X represents the independent variable and Y is dependent variable. When you write Y is equals to f of X, Y is a function of X, so that you can call X as the independent variable and Y as the dependent variable, right? Then see, let me come to the mathematical definition of what a function is, right? So, in colloquial language, you can simply say function is, a kind of representation like Y is equals to f of X. And then whenever you give some input to X, it gives you some output Y, right? So it's a simple way of representing a function. But when you want to represent this mathematically, you will just take you will take them like this. When you have two sets of elements may be numbers or something, whatever you have, whatever you can take. If you take one set as d and the other set as some y, for there may be certain elements like if you take x1, x2, and so on, some xn, and then let us say you have y1, y2, and so on, yn in the second set. Now see, to each element in the first set, if you can find a unique image in the second set, then this relation y is equals to f of x can be taken as a function, right? You can call f of x, or else y is equal to f of x is a relation. In fact, f of x, you can take f of x as a function for each x if you can find a unique y in the second set. See, this relation can be taken as a function, right? So it's a definition which you know already, and I'm just recalling that, right? You can see a function f from set d to y, it is a rule that assigns a unique element f of x belongs to y. See, whatever the f of x you mentioned here in this definition, that f of x is nothing but y1, y2, yn here, right? Because we are defining y is equals to f of x as the function. So when you get some f of x, that is equivalent to this y, right? So when you get a unique element f of x is equals to y in the second set, corresponding to each element x in the first set, then you can call this relation as you can call this as simply a function, right? So that's how you can just remember, you can recall the definition of what a function is. Then see, let me just get into the other details. Then see, when you define a function, there are, as you understood now, there are two sets of elements. The first set you are taking it as some capital D, and the second set you are taking it as some capital Y. All the elements of first set, capital D, we normally call it as a domain, right? And the second set, see, there may be a function of this kind. Let me just understand it this way. You have some capital D with three elements, 1, 2, 3. Then let us say you have some other set of elements, capital Y, like ABC, these three are the elements in capital Y. See, to be a function, if you define a relation here like y is equals to f of x. See, x is an element in this first set, y is an element in the second set. Understand it that way. Then let us say element 1 is mapped to some b, element 2 is mapped to some a, and element 3 is also mapped to, let us say, a. Then see, you can understand, to each element in this first set, there is a unique image in the second set, right? If you have, for example, element 1 has one image b here, along with b, if element 1 has the other image like c also, then you cannot take this as a function, right? If you take any element in the first set, and if you find a unique image in second set, you can then take this relation as a function, right? And now see, from this example, what may be the domain? You are taking domain as set of values from the first set. So that domain is the set D, the elements 1, 2, 3. And see, what you are calling the range here, range is set of all output values. See, corresponding to these values in the domain, what are the images you are getting from the second set? Though there are 3 elements in second set, only 2 elements were mapped by some of these 3. So that the range of this particular function is only a comma b. But what about the second set y? You can call this second set y as a codomain, right? So when you find a relation between 2 sets of elements, the first set is actually domain and the second set is codomain. But within the codomain, if there are few elements were mapped by some elements from first set, then you can call those set of elements together as a range, right? Range is set of all output values and domain is set of all input values. Okay, that's how you can remember it, right? Then see, now how can we recognize a function? That's a question, right? How to identify whether a relation is function or not? There are several ways, but let me just look at this. If you are given some relation from D to Y, how to identify whether it is a function or not mathematically? Right, see exactly there are two conditions. If all the elements in first set are associated to some elements of section Y, I mean set Y, right? The first condition is all elements of D must be associated to some elements of second set. I mean, you cannot leave any element alone in the domain, right? The first condition is every element in the first set must be mapped to some elements in second set. Then see, to each element in first set, there must be a unique image in the second one, right? There must be a unique element in the second set. If any relation satisfies these two conditions, you can take that relation as simply a function. Okay, so understand like this. Then see, let me just go down to this example. Right, see, if you take two sets of people, one set of male and other set of female, look at this. There are 4 male I have considered here, and I'm taking it as some set X. And then you see there are 4 female in set Y. Now see, the relation which I am defining here is every male has their respective wife. Now see, look at this. Male 1 has, his wife as female 4. Male 2 has his wife as, you can see, female 3. Like this, corresponding to each person of this first set, you can find a single image in the second set. That's how you can take this particular relation as a function, right? By chance, as we know, I'm just taking it for a joke. For example, if one male in the first set has a relation with the other one also here like this, he has already a wife, with this name F4. But if he has a relation with the first one also, see, this is illegal, isn't it? So nobody should have 2 people as their wives. That's how this cannot be taken. In this case, it cannot be taken as a function even, right? So for the first set of people, or else for the first set of elements, if you can find a unique image in the second set, then you can call this as a function. And in case you see, there is one more chance. Out of these 4 people, if there is no image for this 4th one, I mean, you see, M4 is actually mapped to F1 here. But if there is no such mapping here, then what happens? See, you are leaving one person from this domain set. In that case also, you cannot take this relation as a function, right? So there are 2 conditions as we are discussing. Every element of this must be associated to some element of second set. And what is the second condition then? For every element in the first set, there must be a unique image in the second set. Then only you can call this as a second set, a function. Then somebody is asking you, what is pre-image? What may be a pre-image? See, when you are speaking from first set to the second set, first set to the second set, we'll speak about the images. You're observing from first set to second set, set X to set Y. Then you will speak about set X has some images in set Y. But when you observe it from the other direction, set Y to set X, some elements of set Y have some pre-images in set X. Normally, when the function is defined from D to Y, elements in Y are taken, elements in Y can be taken as images. And then corresponding to some elements in Y, you can find some pre-images in set D, right? I mean, here in this example, you can take F1 has a pre-image as M4. Because M4 is mapped to F1 here, you can take M4 as a pre-image to F1. Then M1 is a pre-image to F4. Right? So looking at the mapping, you can identify what are the images and what are their pre-images. Then see, let me just draw one simple, what you call, an example of this kind. Just try to identify whether that relation is a function or not. Let me take 2 sets of people to 2 sets of students. Right? I'll come to this again. Now, see, let us say the first set of students I'm taking it as some B, and the second set of students, let us say it is G. And let me take the first set has three elements like, three students like B1, B2, B3. And let us say second set has these three elements, G1, G2, and G3. And if the relation is like this, can you say it is a function? You can respond in your in chart. I'm waiting for you. Yes, yes. Yes, good, good. Yes, it is a function, right? Right. So here is an interesting question. Let me just address about it. One student is asking me if X and Y are two sets, and if we say that Y is equal to f of X, then which one is domain? Set of X value. See, when you write Y is equals to f of X, when you write Y is equals to f of X, it means X is the input. So whatever the values possible to take, to consider for X here, set of all those values can be taken as domain. Right? Set of all possible values which you can take for X here. Right? That is what domain. Then yes, so this relation is a function. Then see, I have one more idea here. In case if it is ignored, right? Let us say B1 in first set is mapped to some G1, and B3 is mapped to G2. Is that a function then? Right? So now it is not a function because you cannot leave any element alone in the first set. Correct? Then, for example, if B2 is also mapped to G2, right? Some student is asking me many one will be considered it as a function. I'll come to this. Right? So here, in fact, you can understand, yes, both B2 and B3 are mapped to G2. Still, B2 has a unique image as G2, and B3, we'll observe this individually. B2 has a single image as G2, and even B3 has also a unique image as B2. Corresponding to B3, there is a single image. Right? Of course, it is G2. I'm not worried about it. I'm just only observing it from one direction. Right? For some element in domain, if there is a unique image, then it is a function to me. Right? In case, you see, if you have like three boys here, sorry, I cannot say boys, but you can understand it. B1, B2, B3 are three students. And if you have three elements in the second set, like G1, G2, G3, by chance, B1 is mapped to G2, right? So B1 has a very close friend G2, even B2 has a close friend G2, B3 has also a close friend like G2. Then is it a function? All the three elements are mapped to something, right? All the three friends have the same common friend here. Still it is a function, it is allowed, right? Somebody was saying about many to one. Yes, you see, this is many to one. Still this is a function here. But see, here is a problem. Let us say you have again three sets of students in first set, and let us say other three students in the second set. Then by chance, if B1 has three friends, and simultaneously B2 has some G2, B3 has some G3, then is it a function? Right? See here, B1 has three images in the second set. So when B1 has more than one image in the second set, then you cannot take this as a function. This is not a function. This is a function. This is also a function, no problem. But when one element in the first set has multiple images in the second set, then you cannot take this as a function. Agreed? So most of you are saying it is no. Yes, this is not a function. Okay, I hope you understood the basic idea of what a function is. Then coming to this first example, right, understood. Now coming to this first example, what may be the domain? right? See, coming to this first set, since all the three elements were mapped to something, you can take domain as B1, B2, B3, right? Corresponding to this first set, the domain is, I mean, the first example, the domain is set of all elements in the first set. But what about the range here in the first example? I'm speaking about this. In the range is, look at this. How many elements were mapped by some of these elements? Though there are three elements, only two elements were mapped, correct? So that the range is only G1 and G2. But the codomain is set of all these three elements. Codomain is G1, G2, G3. Now, if you take the second example, if you take this, right, the domain is again, see, B1, B2, B3. But now in this case, the range, you see, in this example, now the range, see, all the three elements are mapped to only one element G2, so that the range is set of only one element, which is G2. And then if you look at the third example, all the three elements are mapped. In fact, it is not at all a function, isn't it? When it is not a function, you cannot speak simply anything about domain and range, right? That's it. So, superb, very good response. Let's continue the same spirit. Now, see, this is what we are discussing till now. What are domains, codomains, and ranges of any function? Okay. And when you have a function which is defined from D to Y, normally we take D as the domain and capital Y normally taken as codomain, right? Normally, in general, capital Y is called codomain, and in particular, only some elements of Y are related by some elements from capital D. Then we call those set of elements as range. See, this is range. Okay, and this is a mathematical definition which you know, right? So range represents set of all function values corresponding to some element of domain. Then see, let's look at these simple examples. The idea here is, when you are given some set of finite elements, you can easily observe whether that relation is a function or not, right? Looking at two different sets of elements, if they are mapped by some relation, you can easily understand whether that relation is a function or not. But what if you are given a function, like this, right? When you represent a function in terms of some, input function like this, then when you are given this way, how can we identify what are the domains and ranges, right? Now understand, when you are given a function with this idea, you can identify the domain as the set of all values of x where this function exists. Okay, so domain for this function is set of all values of x for which this function exists. What does it mean? You normally take set of all real numbers, right? You will normally take set of all real numbers, and now from this set of all real numbers, you need to exclude the elements for which this function doesn't exist. Okay, so to find the domain, we'll simply understand for what values we cannot use x. I mean, for what values of x this function doesn't exist. And if you can exclude those elements from the set of real numbers, so this set gives you the domain, right? So yeah, as some of you are saying here, when you take x is equals to 0, you will get it as 1 by 0. When it is 1 by 0, you cannot identify that, it is undefined. That's how you cannot take 0 in the domain, right? So just let us see this graphically. So the domain we cannot take, in the domain we cannot take 0 as the element. And if you just observe this, we call this as set builder form, as you know. And see, to write the domain, we need to exclude 0 from the set of real numbers, right? Either you can represent the domain in this way. You can take set of all real numbers except 0. You can take set of all real numbers except 0, or you can even take it like this. Set of real numbers in the sense, the elements from -infinity to +infinity. And if you can exclude this set, right, set containing the element as 0, You will get it like this, right? Minus infinity to 0, union 0 to infinity. So this excludes the element 0, right? So we call this as interval notation, as you know. So the domain for this particular function is actually, this minus infinity to 0, union 0 to infinity. If you just observe this graphically, it looks like this. Right, see, when you observe the graph of 1 by x, as x approaches to 0, you see, when x approaches to 0, either from right side or from left side, you can see. When x approaches to 0 from right side, see the function values are moving up. Function values are moving towards plus infinity. And when x approaches to 0 from the left-hand side, you can see function values are going towards minus infinity. Right? And in the other way, when x approaches to infinity, when x approaches to minus infinity, you see in this way. When x approaches to minus infinity, see the function values are going closer to 0. And when x approaches to plus infinity, in this direction. When x approaches to plus infinity, you can see again the function values are going closer to 0. That's how, as you can see, the domain is set of all real numbers excluding 0. And even the range, since you cannot get function value as 0 for any number, you may get you may get a number which is very much closer to 0, but you cannot get exactly 0 as the function value. So even in the range also, I'm excluding 0. Right? You will get all other function values except 0. Right? You will get all other real numbers as function values except 0. That's how, in this case particularly, both domain and range as same. Okay? Normally, you see one idea. When you are given a graph of this kind, remember, normally we take domain on this x-axis. We take domain on x-axis and range on y-axis. Okay? That's how you can understand it. And you can even identify the domain and range of functions when you are given them like this. Now let's take one more. What may be the domain and range of this function y is equals to root x? Right? Y is equals to root x. Can anybody? I'm getting some responses from chat box. What may be the domain of this function y is equals to root x? To identify the domain, what we need to do is, you see, for what values of x this function exists. If you can identify those numbers, then you can take all those numbers together as the domain. Right? Some of you are saying 0 to infinity. Some of you are saying excluding negative integers. Then somebody said natural numbers, whole numbers only. All right. All positive values. That's great. Right. So one student raised his hand. Right. See, 1055, I'm unmuting you. You can speak. Unmute yourselves.
Sir.
Yeah.
Good morning, sir.
The domain. Good morning.
Sir, non-real negative numbers.
Non-real negative numbers. Good. Right. Fine.
Non-negative.
All right. All right. I got your point. Non-negative real numbers. Right. Right. See, in simple, we can take x as any positive number including 0. X should be greater than or equal to 0. Or some of you are saying even 0 to infinity. Right? So when you say this, you can even include 0. Right? For 0 also no problem, you can find out the square root. So set of, see, I'm speaking about the domain. You cannot calculate square root of a negative number, isn't it? You will get complex numbers, I mean. So I'm not discussing about complex numbers here. When we define a function, we'll take only real values. So in that sense, I can say I cannot take any negative number here. Therefore, the domain must be set of all non-negative real numbers, as somebody said now. Right? You can take all numbers from 0 to infinity. Somebody said actually natural numbers. No, you can take real numbers. Natural numbers in the sense only you'll get these numbers, isn't it? Positive natural numbers. But even you may get any number between 1 and 2. So with that idea, the domain of this particular set is from 0 to infinity. Right? So as you cannot take negative numbers, as you understood now, See, domain is set of all elements from 0 to infinity. You can even include 0. Right? So that is half open interval. And if you just observe the graph, see, it looks like this. Right? Now see, the domain, as you can understand here, set of all positive numbers. Right? You can take all the numbers from starting from 0 to infinity. You cannot take any negative numbers. That's how you can see the graph comes only on one side. Then what may be the range here? That's a question. What may be the range? Do we get set of all real numbers as the range or only something? That's a question. Right? While we are defining the function, what we said, for any input from the domain, you must have a unique image, right, in set Y. Right? See, the relation here is y is equals to root x. If you take some x here, there must be a unique image in set Y. Then only this relation is function. Okay? So with that idea in mind, you can just identify what may be the range. Some said non-negative real numbers is the range. That's in fact true. Normally what happens when we calculate square root of 4, in general, probably you already crossed the original stage. So you normally take root 4 as plus or minus 2. But when I take both the elements, corresponding to this relation, if I take x is equals to 4 here, and if you get the elements in y as both plus or minus 2, what does it mean? Element 4 is mapped to both plus 2 and minus 2. With this, you can say there are two images, which is not allowed again. Right? So to be a function, there must be a unique image. So to be a function now, I cannot take both plus or minus 2. Instead, either I can take only plus 2 or minus 2. Right? In that, keeping that in mind, when this is the domain from 0 to infinity, either I can take only set of positive numbers as the range, or even I can take set of only negative numbers as the range. Right? From this particular graph, if you observe, from this particular graph, if you observe, as the graph is above x-axis, you can see range is set of all positive real numbers here, including 0. Right? Range is set of all positive numbers. You see, that's how you got this graph here above x-axis. Right? So keeping that in mind, you can just understand. In fact, you can take negative numbers also, I don't mind. But as per this graph I'm speaking, so here you can take the range as 0 to infinity. By chance, if you take only negative numbers, then you will get the graph something like this, which is below the x-axis. Right? Then you cannot take it. You cannot take this one. If either you can take only positive numbers or only negative numbers. Right? So that's how you can find out the domain and range of this function. See, when you are given a graph, you are just identifying what are its domain and range. And when you are given a function like this, you are able to draw its corresponding graph also. You can just normally take some random values for x, and you can even calculate its corresponding function values for y, and you can just all those function values to get its corresponding graph. Right? That's how you can normally take the graph. When it is a function, you can easily write its graph. But sometimes you may be given a graph directly. If you are given a graph, then how to identify whether that graph is a function or not? That's a question. Now see, to identify the given graph, whether it is a function or not, we'll just use the vertical line test. I think I have discussed this vertical line test with some students during the last week. But as many are new here, I'm just recalling this. And in fact, this is a part of our syllabus. Now see, when you are given some graph, to identify whether that graph is a function or not, we'll just use this vertical line test. What we do, you see, whenever you are given some graph like this, we'll try to take, the graph may be anything, right? I am not just taking anything. If the graph is something like this, then see, to identify whether this graph is a function or not, we'll normally take a vertical line across this graph. Understand, if this vertical line intersects with the graph at a unique location, if this vertical line intersects with the graph only once, then you can take this graph as a function. right? If, see, you can take the original function as a original graph as a function if vertical line can intersect a graph more than once. If no vertical line intersects the graph more than once, or in simple, if the vertical line crosses the curve only once in all locations, you may take vertical line anywhere over the graph. Anywhere you can take the line, vertical line. In all instances, if the vertical line crosses, any vertical line crosses the graph at only one location, then you can take that graph as a function. Okay. In case if any vertical line crosses the graph at more than one locations, then you cannot take it as a graph. Okay. Now let us take few examples of this and let us try to identify whether they are functions or not. Look at this function. See, the graph of the function is, we don't know what is the function actually, but I gave you some graph of this function. And see, the graph of the function is given in red color, right? Try to respond to me in chart whether this is a function or not. If it is a function, see, if I draw a vertical line somewhere here, this should interact, I mean, this should intersect with the graph at exactly one location. Let me just annotate this. Right. See, if I take a vertical line like this, see in how many locations it is intersecting with the graph. Exactly at one location, you see. That's how, yes, this is a function. If I take the other one, look at this. Is this a function? Right, see, if you take a vertical line, in fact, already here is a vertical line, you can see, as this vertical line is intersecting the original graph at 3 locations. Right, see here, at the origin and even below the origin here. Since it is intersecting the graph at 3 different locations, it is not a function. Correct? Very nice. Very good response from you. Then, look at this. Right, if the vertical line intersects the graph at only one position, it is a function. And see, look at this graph. Right. See, I have a question here. Probably some of you may also have this. Why should I take vertical line here only? If I take a vertical line here, it is intersecting only once, no? Right? Then can I take it as a function? If anybody wants me, if anybody wants to interact with me at this location corresponding to this example, please raise your hand. The first one who raised hand will be given a chance. Okay, I got one response. 140, rule number 1040. Yes.
Sir, I have the same doubt, sir.
Okay, good. Right. See, the question is, please mute yourselves. I'll allow another one then. There is 1018. I'm allowing you. Please unmute yourselves. Yeah, 1018. Can you answer this? Is this a function?
No, sir.
No, but see, when I take a vertical line here, you can see a red line here, but it is intersecting the graph at only one location. Right? No, right? Mute yourselves. Let me allow 2039. Unmute yourselves. Is this a function?
Yes, sir.
Is this a function?
Yes.
Yes. Okay.
Yes, sir. Yes.
Yes. Okay. Let us see. 2062. Unmute yourselves. Is this a function?
Yes, sir.
Is this a function? Okay. Right. So let me clear you this again. Understand, when you are given a graph of this kind, see, you can take vertical line anywhere. Wherever you take the vertical line, it should intersect the graph at only one location. You cannot take vertical line only at one location. You may take vertical line anywhere over the graph. If you take vertical line here, yes, it is intersecting at only one location, agreed. But if I take vertical line here, what happens? See, it is intersecting the graph at two different locations. If I take a vertical line here, you see, yes, it is intersecting at two different locations. In every instance, if any vertical line intersects the graph at only one location, then only it is a function. If it fails at one location, no, it is not a function. Right? Wherever you take the vertical line, yes, you should consider the whole graph, not one simple vertical line. Right? Throughout the graph, wherever you take the vertical line, if that vertical line intersects the graph at only one location, then only it is a function. Right? You simply if you take one vertical line somewhere and if it intersects the graph at only one location, then you cannot simply decide it is a function. Wherever you take the graph, wherever you take the vertical line throughout the graph, it must intersect the graph at only one location. Then only it is a function. But if I take vertical line here for corresponding to this graph, right, then this is not a function. So corresponding to this function now, I can say it is not a function. Right? Since this vertical line, you see, if I take a vertical line around y-axis here, if I take either here or here, you see it intersects at more than one locations. That's how, see, this graph is not a function. Okay? I'm not speaking about the domain and range here because I don't know the actual definition of function. Right? That's one thing. And in fact, when it is not a function, we cannot speak about the range. Then let me take the other one. Right. Identify whether this is a function. Now see, you can take vertical line anywhere, right? Wherever you take it, at every instance, if it crosses the graph at only one location, then only it is a function. Right? But if I take a vertical line somewhere here, or here, or here, at all these instances, you see, it is intersecting the graph at multiple locations. So I cannot take this as a function. So this is also not a function. Agreed? Good. Now let me just go ahead. Yeah, look at this. Is this a function? See this? Is this a function? No, right? So if I take a vertical line here, it is intersecting at two different locations. So you cannot take this as a function. Right? Look at this. Is this a function? Look at this. Yes. So wherever you take a vertical line, yes, it exactly intersects at one location now. You may take it anywhere. That's how, yes, this is a function, but not this. Okay. Then let me give you a few other examples. Look at this. Let me just try to explain you this. For one particular function of this kind, you know, sometimes you may be given an open circle and sometimes you may be given a closed circle like this. What does it mean? See, corresponding to this, there is some x. So corresponding to this x, the function value is not defined at this location. Right? For all other values, very much closer to this. Let us say if this is some a. There may be some numbers which are very much closer to a. But for those values, the function values are very much closer to this. But exactly at a, the function value is not given on this graph. But the function value at a is given on this graph. You see here it is. Right? And when it is closed circle, look at this. Corresponding to this, there may be some, let us say b. Now corresponding to this b, the function value is given exactly here. When it is a closed circle, it is given at this point and it is given here also. Right? Now see, when it is open circle, that number is not included. When it is closed circle, that number is included in simple. Now keeping that in view, if you are given this graph, can I take this as a function? Can I take this as a function? Now see, if I take a vertical line here, you know, even if I exclude these two, if I take a vertical line here, you see it is intersecting at two different locations. So I cannot take this as a function. Yes. Now look at this. Right now, see, as I told you now, corresponding to this number, which is on x-axis, see, you can observe two different function values, but here it is open circle, which means the function value is not included. But see here, this is a closed circle, which means corresponding to this number, the function value is given here. Right? So can I take this as a function? Now see, corresponding, let us say if this is A, corresponding to A, let us say the function value is f of A. From this particular graph, the function value can be taken as this, this is f of A. If the function value for A is f of A, then understand f of A is given on the graph at this location, but here the function value C is not defined. So with that idea, if you take a vertical line anywhere, somewhere before this y-axis, it is all intersecting at one location, but the doubt comes only with this line. But even on this line, here this is an open circle, correct? So that the function value is not, it is not included here over the graph. So definitely this one is also a function. Right? So this is also a function, as here it is an open circle and this is a closed circle. Right? Then if you look at these graphs, so the first one, if you take a vertical line here, this is not a function. If you look at the other one, see here, this is closed and this is open circle. So that if you even draw a vertical line here, what happens you see? If you draw a vertical line here, what happens you see? It passes through these two. But since this is closed and this is open here, you will simply ignore this function value because it is open. So that you can understand this vertical line crosses the function at only one location. So that this is a function here at this location, and even the same thing here also. It is open and this is a closed circle here. So that this pass through the graph, this crosses the graph at only one location, and hence this is also a function. And here you see this parabola, it is absolutely a function. And if you look at the other one, the last one here, since this vertical line crosses the parabola at two different locations, you cannot take this as a function. This is not a function. Right? Then look at this circle. When it is a circle, you are given already a vertical line here. Right? See, the vertical line is crossing the circle at two different locations. Correct? So that you cannot take this as a function. And then if you look at this, right, only upper half circle. Now if you take a vertical line anywhere here, right, it crosses the curve at only one location. So it is a function. Right? Somebody is saying y is equal to x square as a function and y parabola is not a function. In fact, you see, you cannot simply take y is equal to x square as this is the only parabola. Even if you take y square is equal to x, it is also a parabola. Right? So there are two ways. When this is this way, if the parabola is given in this way, it fails to follow vertical line test. That's how it is not a function. But if you are given a parabola of this kind, x square is equals to y, then wherever you draw a vertical line, it crosses the function at only one location. Then you see it is a function in this case, but not in this case. Right? See, when you are given a particular function like y is equals to f of x, you know this x represents input values and y represents output values. Correct? Now, when you are aware of all these input values, keeping all these input values together, you can write its domain. Right? When f of x represents a function, then you can write the domain, and keeping all these function values together, you can write the range of this particular function. Right? So once if you know the input values as well as the output values, keeping them, considering them together, you can write the domain and range of, this particular function. But see, in this particular case, when you are given f of x as a single formula, there are no issues. But there are instances where function may behave in different ways in different parts of the actual domain. Let us say if the actual domain is from 0 to infinity. Okay, you are given one function for which the domain is from 0 to infinity. You can take some pieces from this domain. I mean, you can take some subintervals from this domain. Let us say one subinterval is some 0 to 1, and let us say the other one is like let us say other one is like 1 to some 100. Then let us say the third one is from 100 to infinity. Right? Let us say if the original interval here, the actual domain is it is having three different subparts. And understand, if the function behaves differently in these three intervals individually, right? In 0 to 1, it differs in one way. In 1 to 100, it differs in other way. And it, in the interval 100 to infinity, it differs in a completely different way. When the function behaves in different ways, in different pieces of this original domain, we call such a function as a piecewise function, right? So when it is a piecewise function, to represent this function, we cannot use a single formula as we discussed in the last class. But now in different pieces of this original domain, we'll represent that function with different formulae. That's how we call this particular function as a piecewise function, right? When it is a piecewise function, it behaves differently in different parts of the domain, right? So keeping this simple idea in mind, let us just take an example of this piecewise function, and then let us see how the graph of that piece function, how we can draw the graph of that. We can see the other issues as well. Now let me just go ahead with this definition, this example. Now see, if you take this particular example, you can understand by looking at these input values, input values in the sense what values of x we can choose here, right? X can take different values, as you can see. X may be less than 0 for some function. X may take values between 0 and 1. X may be more than 1 also. When you observe all these things together, you can understand when it is x less than 0, it may be from minus infinity to 0, right? See, there is no equality here. This is one piece from your original domain. Then see, if you look at the second one here, it is from 0 to 1, right? Look at this interval, 0 and 1, both are included in this. That's how you can take this as a closed interval 0 to 1. And in the third one, you see, one is, there is no equality for 1 here. There is no equality for 1 here, correct? So that you will take open 1 to infinity. Now see, the union of these three subintervals is your original domain, right? And if you just take union of all these things, the domain which you'll get is simply minus infinity to plus infinity. Everything is involved. So the original domain is from minus infinity to plus infinity, which is divided into three subsets. Okay, and in each subset, the function is behaving in a different way. In the first half, in the first interval, it is behaving similar to minus x. In the second interval, it is behaving similar to x square. And in the third interval, it is simply a constant, right? So now just understanding all these things, let us try to draw the graph of this particular piecewise function. All right, let's see what happens here. Now see, the first interval what you're considering here is x less than 0. When it is x less than 0, you can understand the interval is from minus infinity to 0. That's how you can see the highlighted area here is minus infinity to 0. And within this part, within this interval, the function is minus x. Understand how the graph may look like in this particular portion. Now see, by chance, if you take x is equals to minus 1, right? If you take x is equals to minus 1, now see, the function definition says it is minus x. So that the function value becomes minus of x itself is minus 1 now. So that it becomes plus 1. So corresponding to x is equals to minus 1, the function value is plus 1 here. Then if you take x is equals to minus 2, then corresponding to this, the function value will be, plus 2. Then when you take x is equals to minus 4, you will get the corresponding function value as some plus 4. Right? So when you join all these points, you are going to get the graph of this first function minus x, right? I'm just trying to see that. See, that's the graph of minus x, that too in only the first half, right? X less than 0. Look at this open circle here, right? Why it is given as open circle? because is equals to 0 is not involved in this first interval, right? What does it mean? X is equal to 0. When x is equals to 0, the function value cannot be calculated from the first function here, because x cannot be 0 from this first subinterval. That's how for all other values very much closer to 0, yes, there is a function value, but exactly at x is equal to 0, we cannot calculate the function value from the first graph. That's how corresponding to this first graph, at x is equals to 0, the function value is given as open circle. What does it mean? That function value cannot be calculated from this first one. Then look at the second interval. Right? Oh, what is this? Yeah. See, come again. Somebody is asking me to repeat this. Right? Repeat this. See why this is an open circle here. This is open circle because you cannot calculate the function value when x is equals to 0. Why you are not calculating that? Because 0 is not involved in the first interval here, right? That's why the function value at 0 is simply excluded from this particular graph, right? Then now if you look at the second one, the second interval here is 0 to 1, right? That's how, see, the highlighted portion is now from 0 to 1. Within this particular portion, see, the function value is given as x square. I mean, the function you are given is x square. So when it is x square, how the graph may look like, right? It's normally a parabola, as you know, right? When it is y is equals to x square, it's a parabola which is symmetric about y axis, isn't it? So when you take x is equals to 0, the function value is 0. In fact, 0 is also involved here. And of course, 1 is also included in this interval. And when you take the function value at 1, see, it's going to be simply plus 1. And it for some value, you know, like if you take 0.5 here, corresponding to 0.5, the function value will be 0.25, something like this. So if you just join all these points, you are going to get a parabola like this, right? See, that is the function in the portion 0 to 1. Now see, if you take the next one, the next interval is x greater than 1, correct? So when x is greater than 1, see, you are going to get all this portion from 1 to right and infinity. But corresponding to all these values in this particular region, simply the function value is given as a constant, correct? So whatever the value of x you may take, corresponding to all the values of x, you are going to get the function values as simply 1. So you can expect a straight line which is x is equal, y is equals to 1 for all the values of x in this interval now. So that, see, you will get the graph like this, right? Now see, that's how when you draw the diagram of a piecewise function, you are going to get something like this. In different portions of this interval, it behaves differently. You see, in the interval from -infinity to 0, it behaves like a straight line. And in the interval corresponding to this function, anyway, I'm speaking about only for this particular function. And in the interval from 0 to 1, it is behaving like a parabola. And in the interval from 1 to infinity, it is behaving like a straight line, right? Since it has different behaviors in different parts of this original domain, you are taking this as a piecewise function, right? So like this, normally we don't ask you to draw the diagram of any piecewise function, but it is just to understand the basic idea of what are piecewise functions. Okay, so whenever you are given a particular function with the different subintervals, you need to draw the diagram, or you can just understand how to draw the diagram of this particular function, right? And what may be the range of this? Can anybody identify? This is, the domain is clear, so that we have drawn the diagram. What may be the range? You can just send me a message in chat. What may be the range? Normally, as I told you, you can take the domain on x-axis and the range normally on y-axis. See, for all the values of x which you can take on x-axis, what are the function values you are getting here? What function values you are getting? Looking at the function values, you can identify what you call the range of this particular function, right? Look at the function values. What function values we have taken? Are they from -infinity to +infinity, or from 0 to 1, or 0 to infinity? What may be? Somebody said positive real numbers. Good. -infinity to 1. Let's see. Right. look at this. Look at what values of y we are using in this particular graph. Right? See, we have not considered any value below this x-axis. I mean, because you have not used any of the negative numbers here, your range will not include any negative number, right? And see, from the first function here, x may take any number which is less than 0. You may go up to infinity, so that you may get even plus infinity in the range. I mean, the function value may be plus infinity also for some number. And see, the function values are getting 0 when x is 0. That's how the range is moving from 0 to infinity in this direction. So that corresponding to this piecewise function, understand, the range is simply 0 to infinity. Right? Domain is anyway from minus infinity to plus infinity, but the range is 0 to infinity. And some of you are saying it is set of all positive real numbers. Agreed. Right? You can speak it in either way. But somebody said it is minus infinity to 1. Please correct yourselves. We have not used, in fact, we didn't get any negative number as the function value here. Right? As no negative number is the function value, you will not get any negative number in the range. Right? That's the basic idea here. Okay, this is one thing about piecewise function. Look at this. When I gave you a function of this kind, you have just tried to draw the diagram of that. Okay. Now see, if I give you a function, if I give you a graph, a diagram, can you exert a function related to that? That's my question now, right? Now see, this is again a piecewise function. I mean, this graph represents a piecewise function. Why I'm saying it is a piecewise function? Because here is a break. Now look at the graph. This graph has a break at 1. Right? Whenever there is a break, then you can call this as a piecewise function. Can you expect what may be the function? Understand it this way. When I say it is a piecewise function, look at the domain first. See, the graph is not involved for any negative number on x-axis. Okay, so the domain will not include any of the negative numbers. That's for sure. Then, so it starts at 0. Then up to 1, it is one thing. See, one subinterval, what you can observe here is 0 to 1. And the second subinterval you can observe here is from 1 to 2. Isn't it? But beyond 2, again, there is no graph. So that the original domain is from 0 to 2. This is one first observation. But as there is a break exactly at 1, your function behaves in one way when x takes values between 0 and 1, right? And it behaves in other way when x takes values between 1 and 2, right? Look at this circle here. See, here is an open circle. What does this mean? You can just take a vertical line here, right? So when x is equals to 1, the function value is included in the graph, of the second line, but not in this. Right? See, both the graphs are on this line, x is equals to 1. But here you have a dotted circle and here you have an open circle. What does it mean? When x is equals to 1, function value is involved in this second graph, but not in this first graph. Okay? That's what you can understand here. That's what you can understand here from this. And see, looking at the graph now, try to identify what are the equations of these two lines. Once if you can understand them, you can just replace them here so that you can write the piecewise function also. Okay, I'm getting some responses. I'll just go through them so that, yeah, I'll try to explain you this again. Don't worry. I'll just try to explain you this way. Right? So one portion, I hope it is clear. The graph is starting from x is equals to 0 to x is equals to 2. Right? Beyond, before x is equal to 0, there is no graph. And after x is equals to 2, there is no graph. So that the original domain is clearly 0 to 2. And here is a break at x is equals to 1. So that the function behaves differently between 0 and 1 and then from 1 to 2. In 0 and 1, it behaves in one way, and in 1 to 2, it behaves in other way. That's one thing what you can observe here. If I just look at this, this is a line passing through this origin and this line 1, 1. Though we are excluding the point 1, 1 exactly, just to get the equation of this line, I can consider this point. So I need to write the equation of a line joining these 2 points. What are those 2 points? One is origin 0, 0, and the other point 1, 1. If I can write the equation of this line, I'll get the equation corresponding to this first graph. Okay. Now, I hope you remember this. When you are given 2 points, x1, y1, then the other point has something like x2, y2. You can write the line joining these 2 points. How it is? You can write like, this with this formula, y minus y1 is equals to, you will write the slope, y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. So using a formula of this kind, you can just understand the equation of line joining those 2 points, and see here, x1, y1 are similar to 0, 0. x2, y2 are similar to 1, 1. So that you will get it like this. Y minus 0 is equals to, see, y2 minus y1, which is 1 minus 0 divided by x2 minus x1 is also 1 minus 0. This is multiplied by x minus 0 again. So if you can simplify this, see what happens. You will get it as y is equal to, all this slope is simply 1, and you will get the equation as simply y is equals to x, right? So what does this mean now? This equation, you see, whatever is passing through origin here, this equation is y is equals to x, right? So what you can understand, the graph, whatever you are given in the interval from 0 to 1 can be represented by this equation, y is equals to x. Okay, so you got 1/2 here. And now look at the second one here, second graph. Now see, the second graph is actually passing through now these 2 points. Can you tell me what may be this point? Right? Can you tell me what may be this equation? I mean, this point. See, it is, x is equals to 1 here, and it is on y-axis. I mean, it is on x-axis. So as we know, when a point is on x-axis, its y coordinate is simply 0. So that this point is 1, 0, and the other point here is 2, 1. Now we need to again, proceed in a similar way to find out the equation of line joining these 2 points, 1, 0 and 2, 1. All right. Now see, I'm just going ahead with a similar formula to find out the equation of the line joining these 2 points, 1, 0 and 2, 1. Can you help me? Now this 1, 0 is similar to x1, y1, and this 2, 1 is similar to x2, y2. Right? So that you'll get it like this. Y minus 0 is equals to y2 minus y1. So it is 1 minus 0 divided by 2 minus 1. y2 minus y1 divided by x2 minus x1 multiplied by x minus 1. So that, see, you will get it like this. Y is equals to 1 minus 0, 1, and 2 minus 1 is also 1. So that this slope is completely 1, and hence you will get the equation as simply y is equals to x minus 1. Right? Right? That's how. We don't want it as a single equation now here, as it behaves differently in 2 different intervals. I'm just writing the final equation here. I mean the equation which represents this graph. I mean the function which represents this graph. So how can I write this? You see, now f of xy, I mean f of x can be written as with 2 different functions. And see, what is the first interval here? X is equal to 0 is involved in this. So that 0 less than or equals to x. See, in the first graph, 1 is not included. See, the function value at 1 is not included. That's how I'm not taking equality for this. I'm just taking it as less than 1. And the second interval, what you can see here is, see, 1 and 2, both are included in the second graph. So that I'm taking 1 less than or equals to x less than or equals to 2. Now, corresponding to the first interval, 0 to 1, the equation what you got is this. You see, y is equals to x. So f of x is equals to x when x takes values between 0 and 1, right? One not included. And see, we got this one. You see, y is equal to x minus 1. Corresponding to these values, where x takes values between 1 and 2, the function can be taken as x minus 1, right? Where x takes values between 1 and 2, where both 1 and 2 are included. So this is how you can get the equation of a function which is given in this graph, right? In fact, whenever you are given any graph of this kind, you can try to get its corresponding function. But see, can we get functions of this kind for every graph? I cannot certainly say yes, right? It is definitely no. See, the problem is whenever you are given some known graphs, right? You know, you are familiar with straight line, you are familiar with parabola, you are familiar with, a kind of circle, right? Ellipse. When you are familiar, when you are given graph with these regular graphs, then you can easily observe its corresponding function. But when you are given a random graph, it's not that easy, right? Somebody is saying why we take x minus 1. Can you raise your hand? 2037. Let me speak to you directly. 2037 52037. Yeah, I'm allowing you to unmute yourselves. Please speak out.
Sir, in the
What?
F
Come
of
again.
Sir, last problem, sir, last line, f of x, x
Why,
minus
why it is x minus 1, right?
yes, sir.
Yeah. నువ్వేమైనా మాట్లాడగలుగుతావా? Can you?
Sir,
Can you tell me why it may be x minus 1?
yes,
As
sir.
how you understood? Did you understand why it is x in the first one here?
Yes, sir. First one understand.
Right, because this graph is passing through origin. You have just calculated a line joining these 2 points 0 0 and 1 1, correct? And hence you got that as y is equals to x. Since you got it as y is equals to x, you have substituted x here in this, correct? And see here in the next interval from 1 to 2. In the interval from 1 to 2, function is given by this graph. And see, we have just tried to calculate the equation of this particular straight line, which is passing through 1 0 and 2 1, right? So when we calculate that, see, we got the equation as y is equals to x minus 1. Since we got the equation as x minus 1, we have substituted x minus 1 here. Am I clear? Okay. Right. Enough. I hope you understood that. Okay. 2036, you have any question? I didn't understand. Right. Still, if anyone have any question in this, if you want to communicate to me, if you want to interact with me, you can just raise your hands. That's good. So let me just go ahead. Right. All these things are okay. Now see. Now let's have a look at what you call symmetry, right? You are already familiar with what is symmetry exactly, right? When you observe it, when you observe a graph from one particular location, if you observe it to be similar on either sides of, either sides of a particular axis or a particular point, you can call this as symmetry, right? If you look at this graph, graph of y is equals to x square, I'm just trying to draw the graph of this particular function for different values of x, right? See, as we know, when you take x is equals to 1, right? If you take the graph of y is equals to x square, and if you take x is equals to 1 particularly, its corresponding function value is 1. When you take x is equals to 2, the corresponding function value is something like 4. Not only this, you see, even if you take x is equals to minus 1, you are going to get the function value as plus 1. For x is equals to minus 2, you see, you are going to get the function value as plus 4, right? So if you just join all these points, you are going to get actually, right, a graph of this kind. Okay, now see, it is a parabola, which you know, correct? Yes. So when it is a parabola, you can understand corresponding to this parabola, y is equals to x square. You can see, you can even observe this. It is exactly symmetric about, this y-axis, right? When you observe this parabola by standing on this y-axis, corresponding to this y-axis, it is similar in either ways. That's how you are calling it as symmetric, right? And see, if you take the other graph like this, if you take a graph of this kind, look at this. Look at this particular function. See what are the terms involved in this particular function. See, you have x power 4, you have x square, you have 1. In fact, you can write 1 as x power 0. Look at these exponents 0, 2, 4. When you are given a polynomial function with even exponents, right? When you are given a polynomial function with even exponents, you will definitely get a function which is symmetric about y-axis, right? Understand, when you are given a polynomial function with even exponents, then always that function is symmetric about y-axis. Probably you are already aware of this, right? Otherwise, when you are given a polynomial function, or else whenever you are given a function which is symmetric about y-axis, you can even call that as an even function. You see, we have just seen one function with even exponents, right? See, whenever you are given a function with all even, whenever you are given a function with the terms which are all even functions again, right? So several combinations of even functions is also taken as an even function, right? Even if you speak it graphically, when a function is symmetric about y-axis, you can call that particular function as even function, right? Understand? When you have symmetry about y-axis, you can simply take that particular graph as, it represents an even function, right? If you just draw the diagram of this particular function like y is equals to x, you had seen y is equals to x square. Y is equals to x square is also a even function. Then if you take y is equals to mod x, do you remember the definition of mod x? Anybody? What is the definition of mod x? Okay, I have some raised hands. Let's see. Yeah, you can unmute yourselves. Good boy. Who is this good boy? May I know your good name?
It will be positive and negative.
That's okay. I'll come to that later. But what will be your good name? Hey, come again. Don't worry. It's not a question. I'm just asking you randomly. Unmute yourselves. No problem. Speak out. What's your name?
Aharnish, sir.
Aharnish, one suggestion before you answer my question. Please don't join with your random names.
Okay, sir. Okay,
You won't get any attendance otherwise, right? Yeah,
Okay.
Please come to this question. You can rename it anyway later. Yeah. What is the definition of mod x?
Positive or negative often.
Okay, that's not okay, right? Let me ask others. 2039. Unmute yourselves. I'm getting responses from chat box. Okay, right. So they are not ready to do this. 1048. Yeah. Yeah. Can you? What is the definition of
minus x when minus x when less than 0 is equal to 0.
Yeah, thank you. Thanks for your answer. In fact, it's not audible. Anyway, I understood you are saying something. Okay, that's fine. Right, see?
It is 0 when x is equal to 0 and x is greater than 0.
All right. All right. See, as somebody is saying, as he is saying, mod x can be taken as minus x for all negative numbers, and it is x simply for all positive values including 0. Right? When x is 0, the function value is also 0. Right? Then see, with this definition, if you just draw the diagram of mod x, how can we write this? You see, for all negative numbers, randomly if you take some -1, If you take x is equals to -1, you'll get the function value corresponding to -1 as minus of -1, because for negative values it is -x. So that the function value you'll get is +1. So this is your function value. Then corresponding to +1, since x is greater than 0 now, you will get the function value as +x, so that corresponding to 1 also it is +1. Then when you take some -2, corresponding to -2, you will get minus of -2, so that 2 is the function value. Then corresponding to +2 again, see the function value is 2. So if you just join all these points, when it is 0 exactly, you will get the function value as also 0. So if you just join all these points, you will get the graph as something like this, right? See, this graph is absolutely symmetric about y-axis again. Since it is symmetric about y-axis, you can understand it as an even function. Okay, so now this is also an even function, y is equals to mod x. Okay, then if you look at the graph of cos x, as we know, cos of -x is also -x. I mean, cos of -x is also plus cos x. And if you just recall, normally how will write mathematically an even function, right? When can we see a function as an even function? If you are given one function as some, let us say f of x, when can we write this as an even function? Whenever f of -x is plus f of x, we'll then write f of x as an even function. In case if f of -x is minus f of x, please wait a second. Right? See, this is how we'll normally define whether a function is even or odd. In fact, we are using the same idea whenever you are getting positive function values even for negative numbers, then you are calling this as an even function, right? There are again the same. And as we know, when you take f of x is equals to cos x, cos of -x is plus cos x, correct? That's how you can even take cos x is equals to cos x as an even function, correct? I got one question here. If a function doesn't change, even if you take xr minus xr, I don't understand here. When the function doesn't change, we'll normally take it as an even function, right? So even if it is an even function, that is definitely what you call an even function, right? See, when it is a constant function, it looks, a graph which is parallel to x-axis. When it is parallel to x-axis, yes, definitely it is symmetric about y-axis. No question. Right? So if you just look at the diagram of cos x, it looks like this. I can just look into this shifting of functions. The name itself giving you some idea. Oh my God. See some interesting question here. 1048. I can allow you to unmute yourselves. Where are you? Can you raise a hand? Yeah. Yeah. You must be in a good network place. You are not audible. Okay. Anyway, I got your question. Please mute.
If it is parallel also, it is even function parallel to x-axis.
Why not? Can't you visualize a constant function? See, if let us say y is equals to 51048. If this is a constant function, what you are given, right? So then how can I draw the diagram of this? I'll just take a coordinate plane, correct? Then for all values on this x-axis, y represents the same number. You see, for example, if this number is what you call 51048, right? So this is the number y 51048 on this y-axis. Then corresponding to all values on x-axis, y value is simply constant. So the line, the constant function, it represents a line parallel to x-axis. When a line is parallel to x-axis, it actually represents an even function, right? let me speak in other way also. When it is a constant function, I can just write it like this. This number multiplied by x to the power of 0. Correct? And see here, this 0 represents an even exponent. That's how also you can call this as an even function. And see, when you have a constant function like this, it is absolutely symmetric about y-axis, isn't it? So that definitely represents an even function. Okay. And then now let me just discuss about shifting of functions. See, as the name gives you some idea here, you are trying to shift the graphs of these functions. Right? You are not directly shifting the functions, but you are just trying to shift the graphs of functions. What do you mean by shifting? Shifting is very much similar to relocation. When you know the graph of a particular function, and if you want to relocate the original graph from its original position to a new position, you are calling it as shifting, right? When it is shifting, you will get a new function from the original function, right? You are just trying to relocate the graph of a function from its original position to a new position. So you are not making any changes in the graph, but you are just shifting it from first position to the second position. That's it. But when you are relocating it, it may be done in 4 ways. Understand? Let us say if the base of original function is here, right? The base of original function is here. Then from this position to, if you want to shift it from this position to a new position, it may be done in 4 ways. You may just shift it upwards. You may move it upwards. You may just scroll it down. You may move it towards left side, or you may move it towards right side. In either of these 4 directions, you can relocate the original graph to a new position, right? And see, when I speak something like this, it looks all right. But how will you get these functions mathematically? In fact, if I shift a graph from this position to somewhere this position, right? If I relocate it to some left side, then see, though the graph looks similar, I cannot give the same mathematical function for both of these two graphs. Understand properly? If I shift one graph from this location to the other location like this, the graph of both of the graphs of both of them, they may look similar, but still mathematically I cannot give the same function, same formula for both of those functions. In fact, when I speak mathematically, this new function, I can obtain this new function from this original function, right? This is absolutely different from, this function, right? And how can we get these new functions when you shift one function from its original position to a new position, right? In what ways actually you can get a new function? That's my question, first of all, right? Shifting of origin is one particular idea is somebody is saying, but the base of the function may not be at origin always. Okay, that's one idea, but understand it this way. How you can get a new function from the original function, right? So you may get a new function. You see, let us say f of x is the function. F of x is one function which you are given. I may get a new function from f of x just by adding a constant to f of x. It may be any constant, maybe positive, negative, anything is okay, right? I know surely f of x is different from f of x plus d. These two are different. If not this way, I can just add a constant to this input value directly. Even this is also a new function for me from this f of x, right? So when you are given one function f of x, you may get a new function from this f of x either of in these 2 ways, by adding a constant directly to f of x or by adding a constant to this input. But see what happens when you add a constant directly to the function values. See, you can expect shift vertically, right? As I said, you see, shift may happen in 4 directions, correct? So shift may happen in 4 directions. If it happens in this direction, I am saying shift happens vertically. If it happens in this direction, either towards left side or towards right side, I'm saying it happens horizontally. So when you add a constant to function value directly, then you can expect the shift in vertical direction. Either it may go up or it may come down. Whereas if you add a constant to the input value, then you can expect the shift to happen in horizontal direction, right? So when you add a constant to the input values, the function may move towards left side or it may move towards right side, right? Let's see how all these things happen mathematically, right? I'll speak about rotation and other things in the next portion. That's what actually scaling, but let me speak about only shifting of functions now. Right. So if you want to shift your graph upward, right, or downwards, of course, but see, when I said this, what we discussed, you see, if you directly add a constant to the function value, then you can observe the changes in vertical direction. I mean, the shift happens in vertical direction. But see, if this d is a positive constant, if you add a positive constant to f of x, then the graph will be shifted upwards by d units. Look at this, the red colored graph. This is the original function here. And see what you are doing here, f of x plus 1. When you add a constant 1 to f of x, see, 1 is positive. When you add 1 to the original function f of x, then the graph will be shifted upwards by 1 unit, right? See, what may be the constant you add? That many units, the graph will be shifted upwards, right? In case if you add a negative constant to f of x, I mean, addition of a negative constant is similar to subtraction of a constant k, positive constant k, right? So when you subtract a constant from f of x, then see, the graph will be shifted downwards by k units, right? Look at this. The red colored one is again the original graph. Now, when you did, you see, like f of x minus 1, the graph is shifted downwards by 1 unit. Look at this. You see here, this is at origin. Now it is at minus 1. See, now here, this is at 0. I mean, 0, and see here, now it is at minus 1. See, this is at 0 again, and here it is minus 1, right? So when you directly add a constant to 1, when you directly add a constant to f of x, then the graph will be shifted up. When you subtract a constant, graph will come down. Okay. Then see, in the other way, if you add a constant to the input itself, right? When you add a constant to input, x plus k kind of things, again, understand this k is positive here. Now see, when you do so, normally what happens? You are shifting x towards right side, right? X is here. When you add x, when you add a k to x, x plus k will be somewhere here, right? It moves right side, but the function values, they move left side. Understand it this way. The red colored graph is here, right? F of x. Now, when you add a constant to k, you will observe a reverse, change. When x moves towards right side, here f of x moves towards left side. That's how you can see the graph will be shifted towards left side. Okay. When you add a positive constant to x, then the graph will be shifted towards left side. And in the other way, when you subtract a constant k from this input value x, you can observe the graph will be shifted towards right side, right? So this is how you can shift any graph from its original position to a new position. So there are exactly 4 ways.